In this video, I'm going to prove how to find the power rule using the limit definition of the derivative. That way, when we move forward, anytime we see a function f of x equals x to the n power, we will be able to just find the derivative without needing to use the limit definition. To warm up, let's recall the limit definition of the derivative. So that's the limit as h approaches 0 of f of x plus h minus f of x over h. Remember that this is just the slope formula. You're taking 2 points. Your first x value is x. Your second x value is a number a little bit bigger than x. You're plugging them both into the equation in order to get the y values. Then you're subtracting the y values in the numerator. And when you subtract x and x plus h in the denominator, you're just left with x. We're going to plug into this formula for the function f of x equals x to the n power. So we replace x with x plus h. So we have x plus h to the n power. And then we just leave x as is, minus x to the n. Our goal here is that we cannot currently plug in 0 for h because we would have 0 divided by 0, which is undefined. Since we have 0 divided by 0, though, we know there's a hole, and there's going to be a way that we can eliminate this h in the denominator, and that is our goal. The first thing that we're going to need to do is expand x plus h to the n power. To expand anything, x plus h to any power, we can use Pascal's triangle. Pascal's triangle gives us the coefficients of the expansion. That's written here in black. And then the variables of the expansion come from the x and the h. Notice in every line, we start with a power of x. That power of x that we start with is the same as the power on the binomial. So in this first line, we have no powers of x. We start with 1, and then 2, and then 3, and then 4. The powers of x decrease as we move through our expansion, so x squared, 1x, 0 x's. The powers of h increase, no h, 1h, 2h. That pattern stays the same no matter what row we're in. So here we have 1x to the 4th. The 4 comes from this 4 here. Then we have 4, 3, 2, 1, 0 for our powers of x. And we have 0, 1, 2, 3, 4 for our powers of h. So now let's think about what would happen if we were to expand x plus h to the n power. We know that the first term will start with 1 because everything in the entire triangle starts with 1. We know that the first term will have x's, no h's, and the exponent on h will be the same as the exponent of our binomial. So the first term will for sure be 1x to the n power. The second term, notice here, this number here, 1, 2, 3, 4, matches the exponent of the binomial. So we know that our second term will have a coefficient of n. Again, that's because when the exponent is 4, the coefficient is 4. When the exponent is 3, the second coefficient is 3. Then we know that we will have 1 less x than we had before because the x's are going down by 1. So it went from 4 to 3, 1 less, n to n minus 1. And then this second term always has one factor of h. So that's everything we know. We know the first term for sure. We know the second term for sure. The third term, we don't know the coefficient. Without knowing the numbers above, you'll remember that the numbers above come from adding these two coefficients. We don't know what the next coefficient will be. We know that we'll have 1 less x and 1 more h, but we don't know the coefficient. That pattern will continue. We'll continue to have unknown coefficients. We'll have 1 less x and 1 more h until we get to the very end where we'll have an unknown coefficient and h to the n power. So let's use that to do our expansion of our limit definition of the derivative. So I'll just write that again. We have the limit as h approaches 0 of x plus h to the n power minus x to the n divided by h. And what we're going to have on our first line here is the limit as h approaches 0. And as we just expanded on the previous screen, we're going to have 1 x to the n power plus n x to the n minus 1 times h plus an unknown term that will have another missing x and an additional h. And again, that pattern will continue. We will be down another x, and we will increase another h until we get to the end where we will have as many h's as we had x's to start. This will all be divided by h. From here, we'll do the limit problem as we always have. So we are going to, oh, I forgot here that we had a minus x to the n. Sorry, I forgot that. That's from right here. So the next thing that we can do is we have 1x to the n here, minus x to the n here, and those two will add up to 0. What we have left now is a whole bunch of terms. And again, there are very many of these. We don't know how many, but all of them have a factor of h. We have 1h, 2h, 3h, and every single continuing factor will have an additional factor of h. So we will have every term will have a factor of h that can be brought out of the numerator. So in the first term, we have h times n x to the n minus 1. The second term, again, we don't know the coefficient. We know that we have x to the n minus 2, and there was 2 h's, so there will still be 1 h left. Same with the following term. We'll have x to the n minus 3. There were 3 h's, but now there will be 2 left. And that pattern will continue all the way to the last term, which will have some unknown number of h's in it. And actually, these parentheses should be here for the entire thing, because the entire thing is being multiplied by that h. I took an h out of every term in the numerator, and I'm left with h times this whole quantity, and then my h divided by h, as always, can make 1. I've now done what my goal was the whole time, which is to get rid of that h in the denominator, because now I can replace all these h's in the numerator with 0. So when I actually go to take the limit, this first term will be n x to the n minus 1. This second term will be 0, because anything times 0, we don't know what it was, this coefficient, but we're multiplying it by 0. This next one will be multiplied by 0. So will every other term for the rest of this numerator, which means that in the end, the answer to this entire limit is just n times x to the n minus 1. Another way to think about it, looking in Pascal's triangle, is that the derivative is always this term right here in your triangle. The first term always winds up becoming 0 because you have the first term right here, and then it adds up to 0 because you always have that same expression right here, no matter what power you're in. The second term, the one that I circled, that becomes your derivative, because when you factor out an h, that term has no factors of h left. That one h factors out, and that term stays. Every other term has at least one h. So when you make h equal 0, every other term just becomes 0, and your final answer is n times x to the n minus 1. And that is the power rule. So if f of x equals x to the n, then the derivative is n times x to the n minus 1.